All right, so finishing up where we left off today during class, just that part B, we talked about it briefly. But the first thing you want to notice is that we are going to test it with the ratio test. We're going to see if, in fact, this converges using the ratio test to see if when it's going to be less than 1. So you do the ratio test, you find out when, on what interval, the ratio will, in fact, be less than 1. So we set that equal to 1. We're forcing it to that interval. What we find out is that when you're dividing by 3 here, 3 is positive, so I can multiply both sides by 3. The absolute value of x is less than 3, so that's our radius. So we'd write that in there. Radius is 3. What that means for our interval is that wherever our center is, in this case the center is 0, it's a Maclaurin series, you're going to add and subtract that radius from the center. So we're going to get negative 3, positive 3. The only question now is it a bracket or a parenthesis? And that comes from testing it in the original series. So you put negative 3 in for x, and you'll find that that makes a negative 1 in parentheses to the nth power. And whenever that value inside parentheses like that, that r value in a geometric series is equal to 1, we know it's divergent. If I go ahead and go in there really fast and I actually erase that negative and do positive 3, the other end of the spectrum there, you'll see that, hey, you know what? It's positive 1. Still, absolute value of r equals 1, so it's divergent on both ends, which means we are going to go with parentheses in both cases. So that is our interval radius is 3. And for part C here, since we're doing a ratio test, it's all absolute value. You can ignore the alternator. This is, you want to do ratio tests, so we're going to do n plus 1 for all the n's. And then what you'll notice is you get a cool kind of cancellation. 2 times n plus 1 plus 1. If you distribute the 2, you actually get 2n plus 3. So let's put that in there. On the bottom, same effect. But the cancellation is great on this one. The x on the top is larger than the x on the bottom by a factor of 2. So we get x squared left. And then on the bottom, you actually get a leftover 2n plus 3 times 2n plus 2. Where this comes from is that the 2n plus 1 factorial on top cancels with the remaining 2n plus 1 factorial that would be on the bottom if I had written out the rest of that function. So those cancel. In the end, here's our limit to infinity on what's left goes to 0, which is less than 1. Awesome, because that converges for the ratio test. And for all real numbers, there's not an x that would not satisfy that condition. N to infinity. So radius is infinity, and there's your interval in correspondence there. And of course, that last one, here's the kind of work. Let me back it up a little bit so you can see that unfold. Ratio test on that last one is great. You can just simply put in n plus 1s if you want. But the biggest deal is, if you look closely, it fails the nth term test and diverges from the start. And that actually means that this is not going to have an interval of convergence because it diverges. So, but if you want to run the ratio test too, just put the n plus 1 term in there over the original with that cancellations. You get this limit to infinity of a definite divergent goes to infinity, which is greater than 0. That's the continue. That's the satisfaction. You have to satisfy a certain contingency, and that is for a ratio test. If it's greater than 0, the whole thing diverges. So, yeah, D is a pretty straightforward one. Now, what I wanted to do is go back, if we had some time, to number 3, or to part B. So if I can pull that up here in a second, I will show you. Okay, so here's that part B again. Now, we did the ratio test, and then I also said in class we could use the root test. So if you do the nth root of this thing, run limit to infinity, what you get is absolute value of x over 3. Again, nth root ends up with absolute values. And we want to make it converge, you have to find where it's less than 1. So again, what we get is this inequality. Multiply both sides by 3. It ends up looking just like our ratio test for, I'm sorry, what did I say here? Backing up here, put a 3 in there. That means our radius is 3, centered at 0. And then we want to do negative 3 to 3, and then test for brackets. You put each value back in like we did before. We found they both diverged. So we have parentheses. So you can do an nth root, a root test, nth root test. The other options are, again, looking at just the geometric series test. If I want to do a geometric series test, same thing is that I know for a geometric series to converge, this value inside here has to be less than 1. So I know that the absolute value of x minus 3 has to be less than 1. I end up writing the same situation each time. That's the condition necessary for a geometric series to converge. We end up with the same result, same interval, everything's the same. So hope that helps. Email with questions, and talk to you soon.